more information in. Chapter 16 is your NMR and mass spec. We officially already covered the mass spec, so this is now just the NMR stuff, and this is just looking at kind of the nuances in NMR. Right? So the big deal with NMR is that you're looking at the magnetic spin of a nucleus. Some nuclei have magnetic moments, okay, or have magnetic aspects to them. Two of those common nuclei are hydrogen and carbon-13. Okay? Hydrogen as in the single element, most common abundant hydrogen, and then carbon-13. So because hydrogen is so widely abundant and particularly common in OChem, we can now use NMR to identify structural aspects because we can figure out where those hydrogens are located. It is also useful for carbon NMR, but you'll notice when we reference the carbon, it was not our standard carbon. It was carbon-13, okay, which means it's a different isotope. Because it is a different isotope, the abundance of that carbon is much, much lower, which means it's a more difficult experiment to run. Okay? Difficult in kind of quotes in really only comparison to hydrogen. There's now less carbon present that responds to the magnetic moment in your sample, which means you have to run the experiment for longer time frames to actually get any usable data. So when we look at proton NMR, you can usually run a decent scan on current technologies. Williams just bought an NMR for, I think, 60 grand, and they can get a spectrum in about 10 seconds. Okay? If we run a carbon spectrum on that instrument, it takes 10 to 20 minutes. Okay? So again, it's not a huge difference, but in the grand scheme of things, that's a pretty significant scale up in time, going from 10 seconds to 10 to 20 minutes. Okay? So it's all about the amount of data that you can pull. So in an individual sample, hydrogen NMR, it's everywhere. Okay? Carbon-13, not quite as ubiquitous, which means it takes longer to pull enough information to actually get some useful structural stuff. Okay? There are other isotopes or other elements out there that you can run NMR on. For those of you potentially moving into biochemistry, nitrogen and I'm pretty sure phosphorus, have isotopes with magnetic moments. Okay? So you could see spectroscopy using those elements as well. Okay? We don't just want to kind of address that out of the gate. So what this is coming back to is magnetic moments. So our nuclei have a spin state. Okay? It is typically referenced as alpha and beta. I tend to just refer to it as arrows being up and down. Okay, so an up and a down state. So if we go through to look at a single hydrogen, what I can go through and do is mess with that polarization. Okay, which way that magnetic moment is aligned. Okay, in a sample that's freely spinning and rotating all over the place, those arrows are now all which directions because the magnet can freely move around in the sample. When we put it inside the NMR instrument, it's a much larger magnet, which then forces those fields to align along the axis of the instrument. Okay? We then hit it with radio waves. The radio waves knock the magnetic moment off axis. Okay? And what we can do is we can detect the time it takes for it to relax back to seeing the external magnet. Okay? So we're looking at a very subtle change in the magnetic field. That's what we detect, and we turn into those signals that you've been interpreting for the last couple weeks. Okay? That is ultimately NMR. Okay? The big thing that comes out of this is that electrons shield the nucleus. Okay? This is why we have like effective nuclear charge and all that fun stuff that you did in Gen Chem. Same thing's happening here in NMR. Those external electrons can hide the nucleus from the magnet. Well, if it hides the nucleus from the magnet, it's going to change the amount of time it takes for it to relax back to being in field. Okay? So what we can do is then correlate that time change back to how many electrons are around the atom. And this can give us an idea about the immediate chemical environment of the hydrogen. Okay? If there's a bunch of electrons around it, we would expect a long, and I'm not positive on that, but longer relaxation time. Okay, if there are no hydrogen or no electrons around it, it relaxes back very, very quickly. Okay? And then it just gets reported out on an instrument. We then interpret all of that to mean those certain things about it. Okay? So we take our magnet, we put our sample in it with all this detector fun stuff, coils, radio waves, fire it up, spits it all out, and we get it printed out as a spectrum. Okay? Awesome amounts of physics and mathematics going behind this. You can study it. There's an awesome professor at ASU that accepts undergrad students for undergraduate purposes or research purposes. Fantastic. They've got an awesome instrument. You're more than welcome to go talk to them if you transfer to ASU. Okay? The instrument itself, okay? You've seen the IR, right? The IR is kind of like this little desk. Okay? The NMR is this whole freaking thing. Okay? Okay? The instrument is actually that big, tall tower. That's where you put your sample. Okay? We're dropping our sample into that. Admittedly, this is a large one. Okay? That 850 is referencing the size of the magnet. Okay? I think it's 850. What are magnets? Teslas? So it's 850 Teslas, I believe. Okay? The kind of default or de facto standard is becoming a 400 megahertz, which is probably about 6 feet tall. Okay? And what is that? Probably a 3-foot diameter. Okay? This 850, that's 2 stories. You need stairs to get up to the top of it. Okay? It has to be stabilized and all balanced out and all that fun stuff. It needs this giant effective supercomputer next to it to help interpret all the data that comes out of it. And that gets funneled into our computer here, which allows us to then interpret and see what we do and print out what we want. Okay? See the big red line on the bottom?
Yeah.
Okay? It's a 850 Tesla magnet. Okay? Or maybe even mega Tesla. I think it might be mega Tesla. I think it's mega Tesla. Okay? Really, really strong magnet, which means when you cross that line, if you happen to be magnetic, you happen to be effed. Okay? And so near these instruments, we have these hardcore lines, and sometimes they aren't actually just tape on the ground. They're actually roped off. Like you can't cross the barrier until you've relieved yourself of any kind of metal. Right? For instance, the guy who runs the instrument broke a hip, or he's an interesting guy. I think he broke it in a rodeo, and had to wait a couple weeks for them to actually ship in titanium joints to replace it because a normal iron one would mean he couldn't work with the instruments anymore. Okay, your credit cards are magnetic. If you bring them near the instrument, you wipe all the data on the credit cards. Okay, so yeah, we have to be a little bit careful around these. Okay, so everything built up around it is magnetic free. Is there a question there?
Wearing like something metal, and you got closer, like put it like really strongly, like rip your hands.
Yes. Right. These instruments are effectively the same thing as MRIs, and you can find like surveillance videos of a tech like wheeling a cart of gas cylinders or something without paying attention. Gas cylinders are magnetic by the MRI instrument. It will grab the gas cylinder and pull it directly out of the air and suck it to the instrument. The same thing will happen here. So if you're wearing metallic jewelry, that could potentially be fatal, if not very, very painful. Okay? So the instrument itself is kind of cool. Almost all of them at this size have to be super cooled. Okay, so we're looking at liquid helium, liquid hydrogen. Hydrogen might be excessive. Liquid helium and liquid nitrogen to help cool things through a series of jackets to keep everything cold enough that the magnet can get up to that field. Okay? So really fascinating that they can work with these things and the data that can get pulled out of them. Okay? So some experimental considerations. Okay? When we're talking about those electrons, okay, the first thing is it's shielding. It's shielding our nucleus. It's shielding it more or less than what? Okay. Well, that one has more electrons around it. More electrons than what? More electrons than not having electrons? Okay. So we need something to standardize and compare it to. Okay, because otherwise all we see is a bunch of peaks with really no frame of reference on what we're comparing them back to. So almost always they include TMS in the sample. Okay? In this case, TMS is added as an internal standard, and it's usually defined as 0. Okay? So when you're looking at an NMR spectrum, you might see a little peak at 0. That little peak is TMS. So that when the data gets spit out, we go through, that's the peak that's TMS. I'm going to mark that as my 0 point. That now gives me chemical shift values for everything else. Okay? Without that standardization, we don't really have a way of comparing spectra or even interpreting their chemical shifts.
What is tetrahydrosilane? Why is that? Well, what is
It's
it?
4 methyl groups bonded to a silicate.
Thank you, Mike.
You're welcome. I'm glad I could be of service.
I mean, is there something, like, is it particularly...
So I believe, and I always get my shielding and deshielding wrong, and I think Christian had it right, so we'll pick on him if he's listening at all. It's okay. Our TMS, I believe, is one of the most shielded, so low numbers is shielded. Is that right? Okay. It's one of the most shielded molecules that we can make, which means anything else will be deshielded from it, and we can now measure off of that. Okay? So silicon has virtually the same electronegativity as carbon, so it's a relatively nonpolar molecule, but it has lots of electrons due to its size. So that means those hydrogens have a significant amount of electron density around them without it getting kind of stolen or shifted away from it, which makes them relatively shielded, which is why that sets up our 0. We bond our hydrogen to anything else, that's now going to deshield it, and it's going to shift from that.
Why that?
Yeah, that's it. That's it. It has to do with the shielding. Okay. Those words up there will then absorb in a more deshielded place. Okay? In the case of our NMR, when we go through and read that, that happens to be to higher ppms. Okay? And typically when you look at your NMR, we read it 0, 14 going this direction. Okay? Where our 0 is our TMS, so we're increasing the deshielding here. So if I only bond my hydrogen to carbons, well, there's now less electrons around them, which means it's more deshielded, and it's now going to show up a little bit to the left. Okay? So we can also throw in other words, because why not? Because all the deshielding and shielding stuff isn't confusing enough. They show up downfield. Downfield, deshielded. Okay? The sample has to tumble and move within this. One of the reasons why is it has to kind of cancel out any kind of rotational aspects. If we look at a chair, we have equatorial and axial. If our molecule doesn't spin, flip, or rotate, what happens? Well, the axial and the equatorial hydrogens are now different from each other, which means we see 2 signals. Okay? This can scaffold out to even simpler structures like butane. Okay? If the molecule can't spin, flip, or rotate, and it's locked in that conformation, anytime it does any kind of weird aspect, each of those hydrogens becomes different, which then means your entire spectrum is now just a mess of lines. Okay? So we need to allow for that spinning and rotation to kind of average out the net results of all of those inconsistencies.
You do that if it's super cool.
The sample is not super cool. The magnet is.
And that you just like is insulated enough.
Yep.
But also,
Okay. There are experiments where you can actually test this to see its validity, and you can change the temperature of your sample, and you can see hydrogens start to appear. For instance, if you took a look at cyclohexane, how many signals would we expect to see?
well, 2.
1, really, because all of those hydrogens are freely exchangeable. I wouldn't be able to tell a difference between them. If, however, I recognize that cyclohexane is actually better represented as a chair, those hydrogens are chemically distinct. One's equatorial and one's axial. Okay? if my molecule is allowed to spin, flip, and rotate, they're interchanging back and forth between those two positions, which means instrument can't tell a difference. If, however, you cool the sample down enough, what happens to that rotation? It stops, which then means I can actually see those two different hydrogens. All right? And there are experiments where they test that. They slowly start dropping the temperature of the individual sample, and you can actually see the difference between an axial and an equatorial hydrogen in the NMR. Under most circumstances, that's not the case. They end up coming out in the exact same state. Okay? So it depends on kind of the level of the question. You get questions where it's how many are here versus how many do you see. Those questions can be very hard to distinguish. Focus on the C aspect. That's going to be the most important part.
How does it work? Is it like an average because they're flipping back and forth? And then
Yeah.
They average out, and so they'll like.
That's exactly it. Is it averages out, and as soon as you cool it down, it slowly starts to segregate the
There's
data.
not like it's 1, 1, 1, 1, then it's a temperature point, like now you're getting 2.
You slowly start to see it separate out.
Okay. Is that something you ever have to take into account on an exam, like the temperature?
No, not on an exam. Never. For this class. Okay? So this means we can only run liquids because it has to move. So I wouldn't be able to test a solid. Right? Well, that would suck. How do I get the solid to become a liquid? I'd have to heat it up, but then that could potentially run into thermal issues with the magnet. So how else could we test the solid? Or you can have a different question.
Yes, a question. Put in a solution to get a liquid.
Yep. But if we put it into a solution, what else are we potentially adding?
Another, what's it called?
More hydrogens or carbons. And if we add more hydrogens and carbons, if we're putting it into that solution, the concentration of that solution or the solvent is now astronomical, which means the intensity of that hydrogen counting is going to be so large, it's probably going to wipe out our ability to interpret anything else. Right? So the solvent we use must not have hydrogens or carbons, depending on which spectra we're doing it. Theoretically, potentially, I've never heard of them doing gases, so I can't answer that question. Right? The solvent we typically use is chloroform or dimethyl sulfoxide. Both of those bring in hydrogens and carbons. So how do we minimize that effect? Okay. And really, I only care about the carbon when running carbon NMR. Okay. So in hydrogen NMR, I care about the hydrogen. So if I looked at the structure for chloroform, how can I make sure I don't have a hydrogen? That is chloroform, by the way.
Can you just know that one will show up in that particular?
So again,
It's a chemical.
if we just know it's going to be there, that's okay. But remember, it's monitoring how much is present. If that's the solvent, how much of that hydrogen is present? A lot, which is going to end up resulting in overwhelming the signal of all of our sample. And so we wouldn't actually be able to detect our sample if we put it in as pure hydrogen. We've actually talked about the correct switch out here. D for deuterium. It is chemically identical-ish to hydrogen. Okay, so it still keeps chloroform. We'd refer to it as deuterated chloroform, okay, because the hydrogen has been swapped out with a deuterium. But the interesting thing about deuterium is it has an extra neutron. Where does the neutron go?
Next to the proton.
In the nucleus. And we're looking at NMR. The end was nuclear. That extra neutron does what to the magnetic moment? It kills it.
Oh.
That now takes chloroform and completely removes it from the spectrum. I don't see it at all. Okay? So that simple addition of deuterium or swap of deuterium for hydrogen means I don't have to worry about seeing that show up at all. The slight caveat to that is that deuterium can come on and off the structure if there's hydrogens readily available, say from like, I don't know, water. Like in the air. So we can't perfectly remove all of the hydrogen. We will always see a little bit of chloroform signal show up because our deuterium isn't that clean. Okay? But it minimizes the signal enough that we can see our compound. That's not a question for this class, but interestingly enough, you can make lots of money isolating deuterium naturally from water, and there's actually a sizable market for it. And it's apparently not that difficult to do. So if you wanted to, you could just start your own deuterium collection cycle at home, just running tap water through your house. And then you could sell off the deuterium from the water. Okay? So due to hydrogen exchange, your chloroform does show up. Okay? It'll show up in two spaces. It'll show up at 7.26 as a singlet. Singlet because there's no neighbors, so I only get one peak. Okay? Or it'll show up in the carbon NMR, okay, at 77.2. How do I know that would be the carbon NMR? Hydrogen NMR is 0 to 14. Carbon NMR is 0 up to 200 plus. Okay? So 77 is falling pretty squarely in the carbon NMR. Right? There it shows up as a triplet. I don't remember the exact reasoning behind it, so let's not stress on that, but you would see 3 peaks centered at 77.2. The other solvent you could use would be DMSO. Notice we don't just call it DMSO, we call it D6 DMSO. D6 because I have to put 6 deuteriums in there. What was the name of DMSO? Dimethyl. Each methyl group has 3 hydrogens, which means 6 hydrogens would have to get swapped out. It would show up at a signal 2.5 as a pentet, okay, or as a heptet in the carbon NMR 39.5. Okay? Don't stress about those numbers, just kind of more for your value. Okay? So the big thing that I actually want out of that is recognizing that chloroform can show up in your spectra, TMS can show up in your spectra. Chloroform shows up about 7.26. TMS should be there as a 0. Okay? If either of them are present in your spectra, okay, for whatever reason, they usually don't get labeled with an integration. Okay, why not?
There's no hydrogens.
If they're showing up in your HNMR, there are hydrogens. Are they part of your sample? No. So that's why we don't integrate them, because we don't want to use that information to interpret. You might see the peak labeled. If you see something at 7.26 and it shows up as a single peak, you should be a little bit nervous about labeling it. Okay? For most spectra that you'll find, that information has been subtracted from the spectra, so you never see it. Okay? So digital spectra don't show them. Okay? It would only be a real spectrum, and even the real spectrums, the technology is getting advanced enough where they're subtracting it out of the sample before you actually visualize it. Okay? So, which gets us to NMR. Yes?
The D6 DMSO.
Yeah?
That one's at 2.5. That can show up. You just have so little of it, the peak tends to be very, very small. And so you see a tiny peak at 2.5, it's nothing. But if you see a big peak at 2.5, you've got something.
And that can be something to worry about. 2.5 and even 7.26, there are lots of things that can show up in that range. You can potentially get overlapping signals, okay, which you may have already seen if you've been doing the practice I asked you to do. The spectra just says something's here. If there's multiple somethings there, it just counts them. And it's just going to overlap all of that data when it spits it out to you. You have to be able to segregate that information apart. Okay? That does mean typically when you're given problems, you have minimal overlaps so that you can interpret it cleaner, but that's not always the case. Okay? When we look at NMR, there's really 4 main categories that you should be evaluating. Okay? Number of signals, chemical shift, integration, and multiplicity. Okay? You should be starting with the number of signals and chemical shift. Everybody should be super, super competent at that right now. Okay? Because the exam is Wednesday. The integration and multiplicity are a little bit more difficult to interpret, and sometimes so difficult they're virtually impossible to interpret. But if you ask an advanced person to help you with spectroscopy, what's the first thing they look at? The integration and multiplicity. That's because there's so much information there, they're jumping immediately to that because they can do all the other stuff internally. You aren't there yet potentially. So make sure you do the easy stuff first, particularly on an exam. You may get an answer, a final answer, without having to do any of the hardcore work. You can get it way early on. So don't ignore the number of signals or the chemical shift. Okay, what is the number of signals? What does that correspond to? The unique hydrogens or carbons, depending on the spectrum you're looking at. Okay? And this could be groupings of peaks. So it's not the number of peaks, it's the number of signals associated with it. Okay? Chemical shift now gets us a little bit more information. It lets us know something about the local environment of that hydrogen or carbon. Remember, when we're looking at carbon and hydrogen NMR, they're looking for where the nuclei is and how fast it spins back. That relaxation rate is based on the electrons around it. More electrons, longer time to relax back. Okay? So that can tell me what's bonded to it. If it's an electronegative element, what has that done? That's removed a lot of that electron density away from the structure, which then means the signal shifts to higher numbers, okay, or downfield, or de-shielded. Okay? So it gives me a rough approximation of what's happening around the hydrogen or carbon. Okay? The next two are now solely for hydrogen NMR. You don't use integration or multiplicity for carbon. Okay? The integration is the ratio of unique hydrogens. Okay? You remember how in mass spec it was counting what particles hit it at that size. If a whole bunch of particles at that weight hit, it got a really tall peak. Same thing's happening in HNMR. Every single hydrogen gets reported in HNMR. If they're chemically the same, that peak now gets taller because there's more things impacting at that chemical shift. Okay? So we can get a taller peak out of it. Okay? However, it's not telling me the number of hydrogen. It's telling me the number of hydrogen that the instrument detected in the sample. How many molecules did you put in the sample? Probably a couple milligrams, which equates out to 10 to the 20th. No, that's probably too high. No, that's actually probably about right. 10 to the 20th molecules. That's a lot of hydrogens. Okay? On top of which, there's no guarantee that the instrument actually detects every single one of those hydrogens in that 10 to the 20. Okay? So the integration is not the number of hydrogens, it's the ratio of hydrogens in your sample. Okay? That ratio works out really well. Sometimes it is the number of hydrogens. And that's why we go, oh, it's the number of hydrogens. It's not, it's the ratio. So be careful with that interpretation. The last one, our multiplicity, also known as our splitting, is the number of different hydrogen neighbors. Okay? A hydrogen is a magnet. Okay? That's why I can detect it in NMR. If I put another magnet near it, would I expect them to interact with each other?
Yes.
Yeah. So what happens when you bring multiple magnets to each other? They like stick or they repel. So we can see that. Multiplicity is talking about that interaction. How does that interaction affect what we see in the spectrum? Okay? Lots of information there, but the interpretation can be very, very difficult. Okay? So leave that alone unless you're confident in everything else. Kind of make sense? Okay, so our number of signals. Okay? The general recommendation I've got is if you built a model, pointed to a particular atom or hydrogen, closed your eyes and threw the atom up in the air and spun flopped, did stuff to it, would you be able to point to the exact same hydrogen or the exact same carbon? Or are you going to get it confused for another one? Okay? If you get it confused for another one, they are chemically the same. Okay? If you can tell them apart, they are now chemically distinct, and they get their own signal. Okay? How chemically distinct are they? Is one bonded to an oxygen and one bonded to a carbon? Well, those are really different, which means what happens to their chemical shift? It's really different. What if one's bonded to a carbon and another one's bonded to a carbon?
Depends on what that carbon is.
They're going to be a lot closer to each other. So when we're talking about unique atoms, we have to be a little bit careful here. What we're talking about is I don't really care what the instrument shows. Are they different? If they are different, we're just looking at the structure of the compound, then you need to identify them as different. Okay? So if you see a question asking for unique atoms, you're only looking at the structure. You don't care what the spectra ends up showing, because the spectra could show that it can't tell a difference between them. That's irrelevant. Okay? You can encounter these kind of sub-classifications which confuse the hell out of me, so don't stress about them. You hear this word homotopic and antiotopic diastereotopic. Okay? Really all these are referencing is, do you see different signals or the same signal? That's about it. If they're diastereotopic, they're unique atoms. If they're an antiotopic or homotopic, you get the exact same signal. You can't tell a difference between them. Okay? That's all I really want out of that. If you want to dig into it more, we can dig into it more outside of class. Okay, so let's take a look at this structure. All I need is one of these. Okay, let's start with the number of signals. How many signals would I expect to see in an HNMR? What are you looking for in an HNMR? Hydrogens. Does anybody see hydrogens? Or for those of you going, oh, I totally know they're there, look at exam 1. There's a question in exam 1 that says how many sigma and pi bonds? 90% of the class got that question wrong. And what did you do? You didn't count the hydrogens. Don't tell me you see the hydrogens. You don't. When you're looking at spectroscopy, particularly HNMR, draw them on. And that's not intended to be a dig. I'm just pointing out the issue. Okay, that's it. That's all I'm trying to do with that. I know it sounds like a dig. Now that we have all of our hydrogens on, note, this one is very often forgotten because we see 3 other bonds and go, oh, that's it. Remember, octets, we have to have our 4th bond. There's our 4th bond out to that carbon. How many different signals do we see? There's 4 different signals. Okay, when I first asked the question, I actually heard someone say 3 because you counted red, blue, and purple and forgot the green. Okay? This is why you should draw the hydrogens on. That can help you differentiate and see those.
I was watching the video and it was talking about chirality and how
I haven't brought that in yet.
Okay.
Okay, so we might expect to see 4 different signals here. Okay? Where would I expect these signals to show up? Okay. Chemical shift, you're saying in the 1 to 2 range. Why? Those are all generally alkanes. What do you want to challenge?
The presence of the chlorine is very electronegative, so it would shift the chemical.
Chlorine's electronegative. It's probably going to suck the electron density away from the carbon, which means the carbon's going to steal it from the green hydrogen, which means the green hydrogen should be de-shielded. We would expect that green hydrogen to shift the furthest on the spectrum. The rest of them might all very well show up in that 0 to 2 range. You actually refined it and called it 1 to 2. It's probably closer than 0 to 2. Okay? So cool. That works. Okay? At that point, that's all we had. Number of unique signals and chemical shift. So we've got it. Okay? But then we had this question of chirality. Okay? Does chirality matter? It matters enough that we had an entire chapter on it. So yes, it does matter. Okay? Are those blue hydrogens identical? No. Okay? That is insanely difficult to see in a 2-dimensional drawing. But if you take the model and build out the model, you will find that you will be able to chemically distinctly identify each of those hydrogens. Why? Because the chlorine and that green hydrogen are locked in those positions. There is no way that the now soon-to-be orange hydrogen can be confused with the blue hydrogen. What does that mean?
They're chemically distinct.
What does that mean? That they're chemically
They're
distinct.
going to show up on two different spots.
I would expect to see more signals. I would expect to get 5 hydrogens out of this, not the 4 that we saw initially. We could make the argument that potentially we could see something out here, but because we have 3 hydrogens, that actually nullifies it and we don't have to worry about it. This is where you could deal with the enantiotopic stuff if you wanted to. Okay? It turns out the blue and the orange ones, let's pick this color. These ones are diastereotopic. Rheotopic. Okay, I got that right. And these ones out here are enantiotopic. Okay? The purple ones, if I've done this right, and who knows, I could easily have screwed it up, end up coming in as homotopic. That chiral atom doesn't translate enough of an effect out to have a significant effect out with this purple one, even if that was a CH2. If it was a CH2, officially they become diastereotopic. Yes, theoretically we'd have to label those as different hydrogens, and it becomes a giant mess. Okay? When it comes with chiral atoms, only identify the very next position, assuming it has at least 3 different things connected.
Because the sigma bond on the 1 carbon can rotate, 3 carbon can't, right? And that's why they're distinct.
All of those sigma bonds can rotate.
But I mean, like, you're always going to have like 1 hydrogen in the same, like, up.
It's
and
because
then
you have these, if you change one of those out, and so this is ultimately when we're talking about enantiotopic and diastereotopic, they're saying make one of those a deuterium. Would you now be able to tell the difference between these two?
Yes.
No, they end up being an antiotopic. Right? Or actually, no, they'd be an antiotopic. You wouldn't be able to distinguish them. Okay? And so that's where that kind of definition system comes in. I am fully, admittedly, shaky on this. Ultimately, I know that that chiral atom makes the CH2, those hydrogens, different. Focus on that. If you want to talk more after class, we can. I don't want to dig more into it because it's a nest of spiders and snakes and venom and stuff we don't want to worry about right before the exam. Okay? Because this is already going to explode things as we move further down the train. Okay? But we need to be able to at least acknowledge that those chiral atoms can have an effect. Not only can, but will in certain circumstances. Those hydrogens are now chemically unique, which makes this a giant freaking mess. Okay? Chemical shift. Okay, we just kind of addressed some of that chemical shift. If we took a look at these 2 compounds, okay, this is a favorite of the ACS and other instructors. I always found this really irritating. Okay? If we go through to look at this, how many hydrogens do you see on that first structure? Okay, the appropriate answer would be 0. Okay? And again, for those of you going, well, I can see it. No, you can't. Just accept that you can't and you have to draw it out. Please. It'll just make life so much easier for everybody if you just make that exception. Okay? How many distinct hydrogens are there? We get 3. Okay? For the other structure, how many would we get?
3 distinct.
We also get 3 distinct. Okay? So according to our number of signals, we would not be able to distinguish these. I guess another question I could have asked, which I forgot to ask, are they different?
Yes.
Okay, yes, they are different. Okay? If you're good with your nomenclature, you should be able to actually name them and recognize the names are different. Okay? So number of signals doesn't help us. What about the chemical shift? Where does the red hydrogen show up? Let's switch that up. Purple hydrogen.
0 to 2.
Next to a carbon.
Okay. It's the 0 to 2 range. This is going to be our alkane. Okay. Now we run into the dicey one, our red and blue carbons. Which one do you want to look at first?
Blue.
I heard blue first. You want to look left or right? Blue, left or right?
Left.
Okay. Where do those hydrogens show up? Why should that be really high?
Because it's near a really electronegative atom.
They're very close to that electronegative oxygen. This causes them to shift significantly. We jump into the 3 to 4 range.
That's the everything else, right?
Okay, which for those of you that studied off the sheet that I've been telling you to work off, that is the everything else range. That's because so much crap falls in that range. I think it's dumb to ask questions forcing people to nuance that difference. I'm in the vast minority with that statement. Okay, so we do have to be able to evaluate that. If we shift over to the blue position on the other side, on the right-hand side of the structure, are they as close to an electronegative element? No. A lot of people go, well, yeah, the oxygen's right there. What's before the oxygen?
Carbon.
A carbon, which means those hydrogens might be shifted a little bit, but there's an extra carbon in the way, which means that chemical shift,
Less than 4.
significantly less or 3 or 4, it actually drops pretty sharply back to that 2 range. It's at the high end of the 2, and you can check me on this, and I could be wrong. Pretty sure it actually falls at 2.1. This is one of those things that I got irritated with enough that I got wrong, that I've memorized the stupid number. Okay? I'm not positive, but I'm pretty dang sure it's 2.1. Okay? If we go over and look at the red carbon, what happened?
Something similar, it's near but not.
It's near, but not too near, versus it's right next to the R3 to 4 range. So when looking at the chemical shifts, I have a signal between 0 and 2, a signal between at 2, and a signal between 3 and 4. Can I tell a difference yet? Okay. If I can tell a difference between the red and the blue hydrogens on my spectra, yes, I can tell a difference. Have we addressed how to tell that difference yet? No. All we've talked about is the number of signals and chemical shift. What extra little layer do we have to look at here? Integration is the next on our list. When we go to integration, it tells us the ratio of hydrogens. If we went through to evaluate the ratio for our leftmost structure, there are 3 hydrogens to 2 hydrogens to 3 hydrogens. Okay? If we look at our rightmost structure, 3 hydrogens to 2, where'd it go? To 3. Not much of a difference, but remember, the chemical shifts haven't been interpreted here. Which one shows up furthest downfield for the left structure? So I would see a 2 followed by a 3 followed by a 3. That would be my integration ratio with respect to our ppms. If I move over to the rightmost structure, what do I have? A 3 to 2 to 3. Do you see a difference now in your integrations? Okay. So it's not even that the integration ratios are allowing us to differentiate. It's the chemical shift, but we have to make sure we tie the chemical shift to the proper structure. Everybody track that? Okay. It is an insane favorite of the ACS to differentiate between esters, because that's what that functional group is, based off of chemical shifts. I think that's a nasty, rude question. But unfortunately, that's all I got. Okay? So our chemical shifts, things will shift further downfield the closer they are to electronegative elements. Okay? There are some other things that can factor into this, like aromatic rings. Can I erase that? If I looked at an aromatic ring, okay, like a benzene, and referenced each of those hydrogens. Well, when we look at each of those hydrogens, what might we say? Okay, they're all the same. So one signal, where should that one signal show up? Okay, we're looking at hydrogens bonded to a carbon. Where does a hydrogen bonded to a carbon typically show up? 0 to 2. It is a double bond, so maybe that causes it to shift a little bit. Why would it shift a little bit? What can you tell me is different between the double bond and the single bond?
The S characteristic?
The S characteristic coming from hybridization. We have an sp2 carbon versus an sp3. We've decreased the hybridization. We've effectively made the carbon more electronegative. Because our carbon is now more electronegative, what happens to the signal? It shifts to the left to a higher number. Okay? It turns out that our pi bonds and rings also have some extra fun stuff going on with them, which I'm sure the textbook has better pictures of. But because of the resonance, there's a huge ring current. Okay? The electrons are constantly oscillating all the way around this. Anybody taken electricity and magnetism class? Okay. If our electrons are moving in one direction, where's the magnetic field? Coming in and out of the plane, which then means our hydrogens, some magnetic mumbo-jumbo, become massively de-shielded. Okay, that's all I got, magnetic mumbo-jumbo.
There's a magnetic.
Okay. There is a magnetic field associated with this, which takes all of the electron density and effectively removes it from the hydrogens, which means they shift to very high numbers. Okay, very high being 7 to 8. Okay, I have seen them drop as low as 6.5, but it's usually in that 7 to 8 range.
What's the higher
Okay.
shift than electronegativity?
It's a higher shift than electronegativity. Yep. Okay. The other thing to be concerned about, okay, when we're looking at chemical shifts, okay, is you may see tables that go through and say, well, the hydrogen bonded to a carbon that is bonded to a chlorine, this one shows up at, anybody know? Like, this is how much I've memorized it. I think it's dumb. I'm just going to say 3. Okay. What if we bond it to another chlorine?
Be a bigger number.
It shifts to a bigger number. What's the number? I don't know. Let's try 5. Okay. It bonds to another chlorine. Oh, now it's going to shift even further. We should know that one. That one shows up at 7.26. Damn. Why are you laughing? That's chloroform. I literally just told you what that chemical shift was. Okay. What if it's bonded to a carbon first and then a chlorine? Well, then it's somewhere between, and you end up getting this weird, stupid delineation between those that then gets overanalyzed. Okay. The idea on chemical shift is blanket statements. If you got a nuance, you got a nuance. But for the most part, you should be very quick with your chemical shifts, kind of like IR. Does the shape fit in the box? Yeah? Cool. Doesn't fit in the box? I don't care. I'm going to move on. Okay? So be careful in over-analyzing the chemical shifts by looking at those tables. Okay. So these are the table or chemical shift ranges that I've memorized that have worked out really, really well for me. That one exception being the stupid ester analogy. Okay? For the most part, these things put you down on luck. Okay? And you can interpret very quickly some information about your structure. Okay? Integration gives you the ratio of our hydrogens. So when we go through and look at this, we have 3 different groups of signals, right? What is different about those signals? The heights. Why would the heights be different?
Ratio, integration.
Why are the heights different?
There's more hydrogens.
There's more hydrogen being accounted for in that signal. Okay? Which is why the area underneath the curve of that signal, which mathematically the area underneath the curve, I believe, is called the integration. Here's calculus. Tells us our ratio of hydrogens. How can that integration information be given to you? One, it could be given to you just like this. I find this insanely frustrating, and it looks like the ACS has stopped doing this. Okay? Because that interpretation is, I know this first one has more hydrogens because it is the tallest. Then I might say, well, this one has more hydrogens than that one because it is taller than it. Turns out that's not the case. This middle one has the same number of hydrogens as the first one. What? Because it's wider. You can't look at just peak height. Integration is both the height of the peak and the width. So you have to evaluate both components in it. Okay? So you have to be a little bit careful with that interpretation on height. If you're forced into it again, you can kind of get forced into it. One option would be to pretend that you could potentially visualize stacking these on top of each other, okay? Which is horrible, but it can give you some idea. Okay? So that is one way you can do it. Another way to do it, really old school, you cut out the paper where the peak is. Then you put it on the balance and you weigh the individual pieces of paper and you compare the papers to each other. You now have a ratio between those. Okay, did they do that? Yes. Okay, that one was new to me. A colleague told me that they did that, or that one's just bizarre. Okay? The way it is sometimes often written is that the computer can calculate the integration for you. And so what you could see would just be a flat line. Why would there be a flat line? What is the area underneath this part of the curve? 0. So it's a flat line. Now what happens? Oh, there's something there. Okay, oh, flat lines again. Oh, there's something there. Oh, there's something there. And what you can now do is then compare each of those to each other. The heights of each of those. This means pulling out a ruler. Not quite as bad as pulling out a balance. Okay? But you could pull out a ruler to then measure the height differences and get a ratio there. Okay? On an actual instrument, what you would do is select that area, okay, and say integrate it. Okay, and it would tell you a number, 2042. And then you say, tell me what this one is. And I did not pick good numbers for this. 964. And then this one, and it would tell me 1,506. Okay? That's saying effectively how many hydrogens it counted. Remember, I want the ratio. So I go through and to get the ratio, what do? Divide by the smallest number. So I divide all of them by 964. It would give me a number. That number theoretically should come out to be a whole number. Okay? Our computer systems have gotten more advanced. Well, they will actually come out, and you could go through and say, this one is 3. Now when I go through and do this one, it goes through and says it is 2.1. And I do this one, and it comes out and it says it is 2.04. I don't know, I just made up numbers. Okay. What does that tell me my ratio is? 2 to 2 to 3. Okay. Last way that it can be reported, this is if you have someone really, really, really nice. For the record, I am not that nice. The only reason I do that is a faculty member at ASU did it a lot. Okay? They're telling you the integration. Not necessarily the number of hydrogens, they're telling you the integration. Okay? Kind of makes sense? Okay. So let's take a look at a quick example. What is the integration ratio for that compound? Those of you that missed that, the thing in the box. Step 1, draw the hydrogens. For those of you being like, I can totally do that math. Not in any of the numbers that I heard shouted out. How many signals? 2. We can split it through the middle. The hydrogens on the outside are the same. Okay. How many red hydrogens? 6. How many purple hydrogens? 2. What's our integration ratio? 3 to 1. That's what would get reported to you is 3 to 1. Okay? The actual compound has a lot more than 4 hydrogens. Okay? But the ratio of hydrogens is 3 to 1. Make sense? Okay. multiplicity, and this is where things just kind of hit the fan, and we just can either blank out of it and not worry about it, okay, and hope everything else comes out fine. That's okay. Okay, I fully expect that. This is why you'll continue to get tested on spectroscopy throughout the semester. You need to be going back and reviewing it and seeing what's going on with it. Okay? So, hydrogens are magnets. Those magnets affect each other. Okay? That's the simplest story here. After that, we encounter this thing known as the 3-bond rule. It's not a 3-bond rule, number one. Okay? And then people often misapply it. Unequivalent hydrogens are neighbors if they are within 3 bonds of each other. Okay? You probably, and I'm going to say pretty definitely, none of you would reference me as a neighbor because none of you, I think, even live on the same street as I live on. Okay? So you're not neighbors. Okay? So you're not going to affect how I live in my home. That's probably not true because I get paranoid. Okay, but that's effectively what we're looking at. We're looking at how those magnets can affect each other. They can only affect each other if they're close enough. Close enough is within 3 bonds. Okay? So let's look at a quick example. Here's a carbon with a hydrogen. Okay? If I looked at the signal for that hydrogen, what I would see first is that, hey, I got a peak. Okay? Because there's a hydrogen there, so I expect to see a signal show up. If within 3 bonds, so there's 1, there's 2, I have a hydrogen. Well, is that within 3 bonds? Yes. Is that a neighbor? This is where it can become tricky. So we'll ignore that question and come back to it in a second. Where's my blue? There it is. 3 bonds. And I now have that hydrogen. Is that hydrogen now a neighbor? Yes. It is within 3 bonds, so it counts as a neighbor. What does that do to the signal? Okay, well, remember, our hydrogen is a magnet. So our black hydrogen can align with the field or against it. What could the blue hydrogen do? The same thing. But now, because it's close enough to the black hydrogen, instead of just being with or against the field, it's going to be with and against the field and that other magnet. Let's see if I did this right. Okay. Those are going, well, that seems kind of weird. Okay. Let's look at the black signal on its own. It was either with or against. The magnitude, the absolute value of your signal. It goes up by 1. It goes down by 1. The magnitude is 1. It's either a positive 1 or a negative 1. The magnitude, just how big is the number? It's 1. So there's a single value. How many peaks do you get? You get 1 peak. That's why we saw our signal as black. When we bring in that blue hydrogen, what happens? This one's now a magnitude of +2. Okay, the next one is a magnitude of -2. If we go down, the bottom one is a magnitude of 0 and 0. How many states got me a 2? 2. How many states got me a 0? 2. Is 2 different from 0? Yes, so 2 signals. What is the intensity of those signals relative to each other? 1 to 1. It's all coming from the spin pairing out of our systems, how those magnets affect each other. You add in more neighbors, you're going to get more spin pairings that come out of it. And you're looking at all the possible probabilities of how the magnet can align, or the hydrogen atom can align with or without the magnet. Okay? You would then count out all those possible states. All the unique numerical values gets you a peak. How many times it shows up counts for its magnitude. In this case, 2 times to 2 times, we get a 1 to 1. And we end up seeing, for one neighbor, 2 peaks. We refer to this as a doublet. Okay? We have to be within those 3 bonds to be considered close enough to show this effect. Okay? So the rule that can come out of this is the neighbors plus 1 equals the number of peaks. Okay? Or done the other way around, the number of peaks minus 1 equals the number of neighbors. The patterning that comes out of it. It's not just the number of peaks, but how they are shaped. No neighbors, you get 1 peak. With 1 peak, there's only 1 intensity. So the intensity is 1. With 1 neighbor, what happens? We get 2 peaks. The possible states that came out of it was 2 to 2, which means our ratio is 1 to 1. With 3 or 2 neighbors, what happens? You get 3 peaks. You go through all the possible states, and what are you going to find? 1 to 2 to 1. 3 neighbors, 1 to 3 to 3 to 1. Okay? That's the peak patterning that comes out of this. What's kind of neat about that is that has already been discovered. That is known as Pascal's triangle. So the splitting patterns that you get from these fall out of Pascal's triangle. Okay? If you don't care, that's fine. You just need to know the splitting patterns. A single peak all by itself is a singlet. 2 peaks. A doublet. Triplet. Quartet. I think this one's a pentet. Pentet. Might be a quintet. I don't remember. A quinjet. 6 peaks hextet. Like only 2 people laughed. Does that mean only 2 people got the reference?
No, we got the reference.
Okay. Ouch.
You chose to.
Fair enough. Right. So you can hear referencing to these. Chemists are lazy, don't like writing out all the words. So sometimes we won't refer to it as singlet. We'll refer to it as S, D, T, Q, P. Okay. So you might see that labeling system also. Okay. Bottom line, within 3 bonds, okay, and you need this peak shape. Okay, and your n plus 1. Okay, that gives you a lot of information because that tells you about who's the neighbor. Okay, so if I was the original signal and I was split into a quartet, what does that mean? I have 3 neighbors. Does that mean all 3 neighbors are in the same house next to me? Maybe. It could also mean I'm in the middle. And on one side I have 2 neighbors, and on the other side I have 1 neighbor. Could also mean I'm in the middle, and there's 3 houses around me, each of them with 1 neighbor. Okay? So there's multiple ways that you can break apart the neighbors. Okay? As a blanket kind of general idea, go the simplest route possible. If I say I have 3 neighbors, it's easiest to think I live at the end of a block and there's 3 people that live next to me. If I go through an interpretation and I later you start realizing there's no way I could be at the end of a block, okay, then you could go through and say, well, maybe you live in the middle, okay, and you have 2 neighbors on one side and 1 neighbor on the other. Okay, but you have to kind of draw that conclusion from the interpretation of the data. And ultimately, the reason you would go there is because your interpretation of the data failed, and you've got to try again. Okay? And that's where spectroscopy becomes challenging. Spectroscopy is like the ultimate science thing. Okay? And for those of you that aren't quite familiar with what that means, science in general gets taught like, oh, it's just easy. We just move our way through it. No, most of science is failure. We go through, we attempt, and we fail miserably at it, and we keep trying. Okay? Spectroscopy is that. If you just decide to give up on the very first attempt, you will have a very hard time with spectroscopy. Okay? You'll also have a very hard time with science, and people should stop telling you science was easy, okay? Or science was not failure. Science is failure. Okay? So spectroscopy will require multiple iterations of cycling through. Sometimes your interpretation is spot on and perfect and you advance. Sometimes it's not. Okay? Ideally, when you practice, encounter the not successful times, because that's going to help you out for when you get to an exam. Okay? Questions about what's up there? I'm going to clear, and we're going to address a couple more things here.
I did have a question.
Yeah, what's up?
The unequivalent hydrogens,
Yep.
that's only if they are not chemically identical?
True.
Okay, so if you have like, yeah, that.
So when we went through and looked at this, you guys told me the blue hydrogen and the black hydrogen were chemically identical, right? Okay. Admittedly, we looked at this, and you were like, no, those are the same, right? Yes, that's what you said. You don't believe me, just rewatch the video. You did. Is the black hydrogen and the blue hydrogen chemically the same?
No, they're different.
They are now different. They're connected to the exact same carbon, and yet they're each going to get their own chemical shift. Why?
Because you can't rotate.
That is a pi bond, and as a pi bond, you cannot rotate. So you remember why we talked about these things about pi bonds and rotations and all that? Here's why it's important. It does show up. That's unit 1. Pi bonds don't rotate. That makes those two hydrogens different from each other. Okay? We are constantly building on older material. Kind of makes sense? Okay, let's throw in the extra caveat. How many hydrogens were in this structure? Unique hydrogens? 5. Why 5? Whoops. The CH2 had 2 different hydrogens. Because? That chiral atom. Okay, so we had 5 different hydrogens here. Okay, this is where splitting can turn into a giant freaking mess. Okay, so we're going to simplify this. Believe it or not, this is actually simplifying it. I'm going to ignore the hydrogens at position 3. Okay, so for all intents and purposes, those hydrogens have disappeared from my analysis. I want to see what happens to the splitting pattern for the green hydrogens. So here's my green hydrogens. Ta-da, green. Number 1, do I have a signal? Is there a green hydrogen? Yes, so there's a signal. Okay. How many neighbors does the green hydrogen have? 2. There's the red hydrogen and the orange hydrogen. Okay. Since I saw a little bit of puzzled faces, let's go through and draw those in. Red hydrogen, green hydrogen, orange hydrogen. And remember, I said to ignore these. You'll understand why I want to ignore those in just a second. Okay. So that green hydrogen sees the red hydrogen. Goes, ah, you're a neighbor. What happens to my signal?
You get another peak.
I don't get another peak. The peak splits. Okay? And I get 2 peaks. I get 2 signals. This green peak that we see is really the average in between. Okay, so what's happening is our magnet is strong enough to disassemble that splitting pattern so that we can see it. Okay? But some of you might say, doesn't it have 2 neighbors because the orange one is also a neighbor? Is the orange one different than the red one? Yes. Why? The orange one's bonded to a carbon with hydrogens. The red one's bonded to a carbon with chlorine. So those are different hydrogens. Okay? Because they are different, they can't both split the signal at the same time because they're different signals. They're different hydrogens. So now that my signal split because the red hydrogen, what happens? Well, now my green hydrogen sees the orange hydrogen. And it goes, oh, I have another neighbor. What happens to the signal? It splits again. But now what are we splitting? Are we splitting the green signal or the red signal? We're splitting the red. Which means I get 4 peaks. For those of you saying that sounds good, I agree. I'm waiting for spring break. If you don't get it, don't worry about it. I get 4 signals. What is the intensity of all 4 signals? 1 to 1 to 1, because they're all doublets. They're all 1 to 1. So this is not a quartet, because a quartet is short, tall, tall, short. Not a quartet. It doesn't match the peak patterning. We're getting something weird and different. That peak patterning is known as a doublet. But that would just be 2 peaks. That's because it's a doublet of a doublet. Remember how I said we still had the black hydrogens out there? How many neighbors are out there? 3. Did I factor those into this? No. If it sees those 3 neighbors, since those are all identical, those would all split uniquely, or the same, because they're all identical, and what would my signal split into? 3 neighbors means a quartet, 4 peaks. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. For those of you saying, oh my God, yes. Okay. What this is known as is splitting of splitting. Okay. If you have different hydrogens, and this is where it comes in, you have to have significantly different enough hydrogens to force this to happen. If they aren't significantly different enough, those signals don't segregate from each other. If they don't segregate, what happens? They start to overlap. Well, if those 2 short peaks overlapped with each other, what happens? It becomes, they don't disappear. They become 1 taller peak. So depending on the power of the magnet, you may not see all of the complex splitting. Okay? What you may just see instead would be where someone goes through, if they're nice enough, and just says, it's a multiplet. There's just a bunch of peaks. Okay? When you go through to interpret and you see that, that's okay. Don't go through and try and say how many neighbors there are, because you can't. Okay? What you need to do is work without the splitting information. Look at your final structure. Does your final structure encounter something like this? Then that probably explains why you're seeing a giant F, okay, in your spectra. Kind of makes sense? Okay. So that is your complex splitting patterns. You can also see something known as long distance splitting. It usually centers on pi bonds. So we can expand the 3 bond rule to 3 sigma bonds and 1 pi. Super rare, but it can happen, and it usually happens around aromatic rings. Okay? I'm just going to put it on the slide. You're not getting texted on this next part. Okay? Coupling constant. When we talk about how those split, the coupling constant is the distance between the peaks. Okay? That is due to neighbors. Okay? And it is unique to that neighbor. Because it is unique to that neighbor, I can compare the splitting and I can match signals to each other. Okay? Which is really just a fancy way of saying I can do some really cool stuff. Okay? Where it really gets used is distinguishing double bonds. Okay? In this case, I have a cis double bond. The coupling constant is 7 to 12. If I switch to a trans double bond, the coupling constant is 13 to 18. The numerical value changes. Okay? Because that value changes, I can now use that to interpret structure. I think there's a question in the smart work that asks about it because it's kind of a neat topic. We'll never test on it. Okay? With that, we are done.